March 8, 1970, Long Beach, California. If you were there, you wouldn't just hear the noise, you'd feel it in the marrow of your bones. That specific, chest-compressing thump of a supercharged Hemi engine running on nitromethane. It's a sound that doesn't really exist anywhere else in nature. It is violence, controlled and directed, screaming through 8 cylinders. And on this particular Sunday at the Lions drag strip, that violence was about to stop being controlled. Don Garlits, the man they called Big Daddy, the patriarch of the sport, was strapping himself into a machine that was effectively a bomb on wheels. He was sitting in a front-engine top-fuel dragster, a design known affectionately and terrifyingly as a slingshot. This is legacy motoring, and I spend way too much time thinking about the engineering that keeps drivers alive at 300 miles per hour. If you're someone who loves the history of speed, the mechanics of horsepower, or just stories about human resilience, make sure to hit the subscribe button and give this video a thumbs up if this helps you out. Now, to understand why this specific day in 1970 matters, you have to understand the machine. The slingshot dragster wasn't just a car, it was a philosophy. For decades, the accepted wisdom in drag racing was simple. You put the engine in the front, you put the big tires in the back, and you put the driver wherever they fit. Usually that meant hanging off the back bumper, literally behind the rear axle. Look, imagine sitting in a chair. Now imagine that right between your ankles is a differential gear spinning at thousands of RPM. Right in your lap is a clutch assembly that's trying to transfer 2,500 horsepower. And right in front of your face, close enough to fog up your goggles with heat, is a supercharged engine that's barely contained chaos. That was the office of a top fuel driver in the 1960s. Here's the thing, it worked. It worked really, really well. The weight of the engine over the rear wheels gave these cars incredible traction. They launched hard, they went straight, mostly. And because the driver was sitting all the way at the back, they could see the whole car in front of them, which helped with aiming the thing down the quarter mile. But there was a trade-off. There's always a trade-off in engineering, right? The trade-off here was that the driver was sitting in the spray zone. If the engine blew up, you were bathed in oil and fire. If the clutch exploded, you were in the path of the shrapnel. And in 1970, clutches exploded. A lot. You have to remember, the material science back then wasn't what it is today. They were pushing these cast iron parts harder than the metallurgists ever intended. A top fuel clutch in 1970 was a multi-disc centrifugal unit. It had to slip just enough to get the car moving without smoking the tires, but then lock up hard enough to transmit all that power as the car accelerated. The friction generated inside that clutch housing was intense. We're talking temperatures that could warp steel in seconds. When you spin a heavy steel disc at 8,000 or 9,000 RPM and subject it to that kind of heat and stress, physics starts to get mean. The metal doesn't just fail, it disintegrates. And when it disintegrates, it comes apart with the energy of a grenade. Now, you might be thinking, why didn't they just put armor around it? Well, they tried. They had scatter shields, they had blankets, but you're dealing with chunks of steel moving at supersonic speeds. A scatter shield might stop the small stuff, but if the flywheel lets go, it's like a saw saw going through butter. And remember where the driver is sitting, legs straddling the transmission, feet right next to the bell housing. It was a design that practically guaranteed that if something went wrong with the driveline, the pilot was going to pay the price. This brings us back to Don Garlits. By 1970, Garlits was already a legend. He'd won everything. He'd built the cars, tuned the engines, and driven them to victory. He was a master of the front-engine dragster. He knew the quirks, its rhythms, and its dangers better than anyone alive. But even he couldn't outrun the statistics. Here's what most people don't realize about professional motorsport. It's a numbers game. You can be the best driver in the world, you can have the best reactions, you can have the best team, but if you run a mechanical component to its failure point enough times, eventually it's going to fail. And on that afternoon at Lions drag strip, the number came up. Garlits staged a car, Swamp Rat 13, a beautiful machine, long and menacing. The lights on the Christmas tree dropped. Yellow, 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 Green. Garlits mashed the throttle. The butterflies in the injection hat snapped open. The engine roared. The car leaped forward. And then, boom. It wasn't an engine explosion. It was the transmission. The distinct, sickening crack of metal shearing under load. The transmission, specifically the two-speed unit they were experimenting with, overheated and seized. The momentum of the engine kept spinning the input shaft, but the output shaft was stopped dead. Something had to give. The unit exploded. And because of the design of the slingshot Dragster, that explosion happened right between Don Garlits' speed. The carnage was instantaneous. The car literally broke in half. The chassis tubes were severed. The cockpit tumbled. But the worst part was the shrapnel. A piece of the transmission sliced through the cockpit and took the front half of Garlits' right foot with it. Just gone. He tumbled to a stop. The safety crews rushed in. They pulled him out of the wreckage. He was conscious. He was in shock, but he was awake. He looked down at his boot and saw the blood. He saw the damage. And in that moment, as the adrenaline faded and the pain started to set in, most people would have thought about retirement. Most people would have thought, I've had a good run. I'm rich. I'm famous. Why keep doing this? But Don Garlits isn't most people. And this is where it gets really interesting. While he was lying on the stretcher, while they were loading him into the ambulance, his brain wasn't processing the trauma. It was processing the geometry. He was looking at the wreckage of Swamp Rat 13, and he wasn't seeing a tragedy. He was seeing a data point. He was seeing definitive proof that the front engine design was a dead end. It wasn't a sudden realization exactly. People had talked about putting the engine in the back before. It wasn't a new idea. The Germans had done it with the Auto Union Grand Prix cars in the 1930s. Cooper had revolutionized Formula One with rear engine cars in the late 50s. Even in drag racing, there had been attempts, but they had all been failures. They were squirrely, they were unstable, they just didn't hook up. The consensus in the pit lanes was that you couldn't put a top fuel engine behind the driver because you couldn't get enough weight on the rear tires to launch. The physics, they said, didn't work. But lying in that hospital bed in Long Beach, staring at the ceiling, high on painkillers and low on blood, Don Garlits started to do the math in his head. He realized that the problem with the previous rear engine attempts wasn't the location of the engine. It was the steering geometry. It was the wheelbase. It was the balance. He realized that everyone had been building rear engine cars wrong because they were trying to make them drive like front engine cars. They were trying to force a new paradigm into an old box. Think of it like this. Imagine you spent your whole life throwing a baseball. You know exactly how it feels, how it leaves your hand, how it curves. Then someone hands you a frisbee. If you try to throw the frisbee using the exact same motion you use for a baseball, it's going to flutter and crash. It's not the frisbee's fault. It's your technique. The previous builders have been trying to throw a frisbee like a baseball. Garlits, in his haze of pain, started to wonder what would happen if he just learned to throw the frisbee. He called his wife Pat. He told her he wasn't quitting. He told her he was going to build a new car, and he told her exactly what it was going to look like. I'm going to put the engine behind me, he said. I'm never going to sit behind a bomb again. It's one thing to have a revelation in a hospital bed. It's another thing entirely to drag yourself into a wheelchair, go back to your shop, and convince your team to build a car that everyone says is impossible. Because that's exactly what happened. Don Garlits wasn't just fighting an injury. He was fighting the collected wisdom of the entire drag racing world. When he got back to Seffner, Florida, his foot still bandaged and throbbing, the mood in the shop wasn't exactly electric. His main fabricator, Connie Swingle, a genius with a welder but a pragmatist at heart, looked at the drawings and basically said, "Don, you're crazy." Swingle had seen rear-engine cars try to run before. They were death traps. They'd launch hard, get squirrely at half track, and then either spin out or flip over. The physics seemed irrefutable. Without the engine's weight over the rear axle, you couldn't get traction. And without the driver sitting over the rear wheels to feel what the car was doing, you were driving blind. But Garlits insisted. He had this vision of a long, tapered nose, a cockpit that sat low in front of the engine, and a roll cage that actually protected the driver instead of just being a suggestion. He called it Swamp Rat 14. Here's the thing. Building Swamp Rat 14 wasn't just about moving the engine. It was about rethinking the entire geometry of a dragster. In a front-engine car, the steering was fast, twitchy even. You needed that because a short wheelbase meant things happened quickly. If the car started to drift, you had milliseconds to catch it. Garlits realized that a rear-engine car, with its longer wheelbase and different weight distribution, would need slower steering. If you put a quick steering box in a rear-engine car, the driver would overcorrect constantly. It'd be like trying to balance a broom on your finger while someone is shaking your arm. So they started welding. They stretched the chassis, they moved the driver forward, way forward. Suddenly, the view from the cockpit wasn't of a supercharger and headers, it was of the track, just open asphalt. For a driver used to peering around a massive engine block, this must have felt terrifyingly exposed. It was like flying a plane without a nose cone. Now, you might be thinking, did it work right out of the box? Absolutely not. The first tests were, well, let's call them educational. The car was weird. It handled differently, it launched differently. The team, Swingle, Lemons, and Garlits, spent weeks tweaking the setup. They played with wing angles, they messed with tire pressures, they adjusted the clutch slip. But slowly, painfully, they started to dial it in. The debut happened at a local track in Tampa. It wasn't a national event with cameras and thousands of fans. It was a quiet test session. Garlits strapped in, he got a burnout, the car felt stable, he staged, and then he made a pass. It wasn't a record breaker, but it went straight. And more importantly, when the parachute blossomed at the end of the track, Don Garlits climbed out with 2 intact feet. The real test came when they took it to the big leagues, the NHRA Nationals. The skepticism was thick enough to cut with a knife. Other drivers looked at Swamp Rat 14 and laughed. They called it a doorstop. They said it looked like a vacuum cleaner. They said Garlits had lost his nerve after the accident and built a safety car that would never be competitive. And honestly, for a while, it looked like they might be right. The car was consistent, but it wasn't dominating. It was okay. But then something clicked. Garlits and his team figured out the aerodynamics. See, in a front-engine car, the dirty air coming off the headers and the engine disturbed the airflow over the rear tires. In the rear-engine car, the air hit the rear wing cleanly. This meant they could run more downforce with less drag. Suddenly, the car started picking up speed in the back half of the track like nothing else out there. By 1971, the laughter had stopped. At the NHRA Winter Nationals in Pomona, Garlits rolled Swamp Rat 14 to the line. He qualified number 1. He mowed through the field like a scythe. In the final, he faced Kenny Safford in a traditional front-engine dragster. The light went green. Safford got the jump, but by half-track, the black rear-engine machine was pulling away. Garlits crossed the line first, setting a new class record. He got out of the car in the winner's circle, and the silence was deafening. The other teams weren't cheering. They were doing math. They were realizing that their expensive, beautiful front-engine dragsters, the cars they had spent years perfecting, were instantly obsolete. Here's what most people don't realize about paradigm shifts in technology. They don't happen gradually. They happen all at once. It's like a dam breaking. One day, the front-engine car is the standard. The next day, it's a museum piece. But the transition wasn't smooth. A lot of drivers hated the new cars. They hated the way they felt. They said they couldn't feel the car anymore because the engine wasn't vibrating directly into their spine. They complained about the steering being too slow. They complained about the visibility being too good. They missed the reference points of the engine block. And let's be honest, there were still problems. The early rear-engine cars had a tendency to do massive wheel stands. Without that heavy engine over the front axle, the nose wanted to lift. If you got too much air under the front wing, the car would literally take off like an airplane. We saw some spectacular crashes in the early 70s where dragsters would launch, go vertical, and blow over backwards at 200 miles per hour. It was terrifying. So the engineers had to go back to the drawing board. They added wheelie bars, long, spindly structures sticking out the back to keep the nose down. They refined the front wings to generate more downforce earlier in the run. They played with ballast, adding lead weight to the nose to keep it planted. It was a constant game of cat and mouse with physics. And through it all, Garlits kept winning. He wasn't just winning races, he was winning championships. In 1971, he won the Winter Nationals and the Spring Nationals. In 1972, he dominated the Gator Nationals. The rear-engine revolution was undeniable. But there was a darker side to this progress. Not everyone adapted. Some of the older drivers, the legends of the 60s, just couldn't get the hang of the new layout. Their reflexes were tuned to the slingshots. When the car got out of shape, their instinct was to countersteer quickly. In a rear-engine car, that quick countersteer would send you to the wall. You had to be smoother. You had to trust the car more. A lot of careers ended in the early 70s simply because drivers couldn't or wouldn't adapt to the new reality. This is where it gets really interesting. The statistics from this era are staggering. In 1970, 100% of the top fuel field was front engine. By 1973, just 3 years later, over 80% of the field was rear engine. By 1975, a front engine car hadn't qualified for a national event in 2 years. Think about the speed of adoption. And the automotive world, usually changes take a decade. Airbags, ABS, fuel injection, these things took years to become standard. The rear-engine Dragster took over the sport in 36 months. Why? Because it wasn't just safer. It was faster. And in racing, speed is the ultimate argument. You can argue about tradition, you can argue about real driving, but you can't argue with a timing slip that says you just went 240 miles per hour in 6.2 seconds. Garlits had proven his point. He had saved his own life, and in doing so, he had saved the lives of countless other drivers. But he wasn't done yet. See, the thing about innovators is that they're never satisfied. Once the rear-engine design was established, Garlits started looking for the next edge, and he found it in a place nobody expected: the clutch. Remember how the clutch explosion started this whole story? Well, the rear-engine design moved the explosion behind the driver, which was great for survival. But it didn't stop the explosions. Clutches were still failing, and when they failed in a rear-engine car, they often took out the rear tires, the wing, and the parachute lines. You'd survive the blast, but then you'd be careening down the track at 250 miles per hour with no brakes and no steering. Garlits looked at this and said, okay, we fixed the location, now let's fix the component. Here's the thing, when you move the engine behind the driver, you change the entire physics of the vehicle. It's not just about safety anymore, it's about energy management. In the old slingshots, the driver was sitting over the rear axle, which meant they could feel every slip of the tire. They drove by the seat of their pants. Literally. If the car broke traction, they felt it in their spine before their eyes even registered the smoke. But in a rear-engine car, the driver is 15 feet forward. They're isolated. By the time they feel the car slide, it's already happening. This forced the complete evolution in how these cars were driven. Drivers couldn't rely on that visceral, instant feedback loop anymore. They had to drive with their eyes. They had to trust the chassis. And because the wheelbase was getting longer, stretching out to 200, 220, eventually 300 inches, the cars became more stable, like an arrow. A front-engine car is like throwing a hammer handle first. It wants to swap ends. A rear-engine car is like throwing a dart. The weight is where it should be. Now, you might be thinking, if it was so much better, why didn't everyone switch immediately in 1971? Well, money and ego. A top-tier front-engine dragster in 1970 cost about $15,000 to build, which is about $115,000 in today's money. Teams had mortgages on these cars. Sponsors had their logos painted on the cowlings. You couldn't just throw it in the dumpster because Don Garlits had a good weekend. So for about 3 years, you had this incredible era of mixed combat. You'd see the old-school, fire-breathing slingshots lining up against the weird insect-like rear-engine cars. It was the past versus the future, playing out in 6-second bursts. But the stopwatch doesn't care about your mortgage. The rear-engine cars were consistently running quicker elapsed times. Why? Aerodynamics. Look, a top fuel engine is a break. It has a massive blower, header sticking out the sides, and injector scoops that look like mailboxes. In a front engine car, all that dirty, turbulent air was hitting the driver, the roll cage, and the rear tires. It was an aerodynamic nightmare. In the rear engine design, the front of the car was a needle. The air hit a smooth, tapered nose, flowed over the driver's canopy, which was much lower, and then fed clean, undisturbed air directly into the injector scoop and onto the rear wing. This is where it gets really interesting. Clean air is heavy air. It pushes down harder. The rear wings on the new cars were generating hundreds of pounds more downforce than the old ones, simply because the air hitting them wasn't chopped up by the driver's helmet and the engine block. More downforce meant they could apply more power earlier in the run without smoking the tires. By 1975, the war was over. Don Garlits won the NHRA World Championship again, and this time, nobody was laughing. He had effectively extincted the very machine he helped create. The front-engine top-fuel Dragster, the icon of 1960s American horsepower, was dead. It was relegated to museums and exhibition shows. But Garlits wasn't done. The rear engine layout opened the door to speeds that were previously considered scientifically impossible. In the front engine era, 230 miles per hour was the ceiling. It was terrifyingly fast. But with the stability of the long wheelbase rear engine cars, they started pushing 240, then 250. Here's what most people don't realize about drag racing at this level. Air turns into a solid wall. At 250 miles per hour, the air resistance increases with the square of the speed. To go twice as fast, you don't need twice the power. You need 8 times the power. The rear engine car was slippery enough to punch a hole in that wall. In 1975, Garlits broke the 250 mile per hour barrier, then the 260, then the 270. It was an arms race of engineering, and the clutch technology, the very thing that maimed him, had to keep up. The clutch in a modern top fuel car is a mechanical computer. It's not like the clutch in your Honda Civic. It's a multi-stage centrifugal device with titanium plates and sintered iron discs. It's designed to slip. If it locked up instantly at the starting line, the tires would just vaporize, or the engine would bog down and die. It has to slip exactly enough to keep the engine at its peak torque RPM while the tires catch up to the track speed. It's a controlled failure. Garlits and his team, along with innovators like Crower and Lenko, started refining this controlled slip. They used pneumatic timers to add weight to the clutch fingers as the car went down the track. At the launch, the clutch might only be applying 1,000 pounds of clamp load. By half-track, as the downforce kicked in and the tires gripped harder, the timers would slam more weight onto the pressure plate, increasing the clamp load to 3,000 or 4,000 pounds. It was brilliant. It allowed them to harness the massive horsepower of the Hemi without breaking parts or feet. But let's talk about the human element for a second. Imagine being Don Garlits. You've changed the sport. You've proven everyone wrong. You're in your 40s. Most drivers retire by then. Their reflexes slow down, their eyesight fades, but Garlits kept going. Why? Because the rear engine car extended the career lifespan of a driver. It was physically less punishing. You weren't breathing nitro fumes directly. You weren't getting battered by oil spray. You were sitting in a relatively calm cockpit. This allowed Garlits to race well into his 50s and 60s. He wasn't just a participant, he was competitive. In 1986, at the age of 54, he built Swamp Rat 30, a streamlined, fully enclosed cockpit car that looked like something from Star Wars. He took it to the Gator Nationals and blew everyone's doors off. He broke the 270 mile per hour barrier in a car that he designed, built, and tuned himself. Think about that. In 1970, he lost half his foot. 16 years later, he was the fastest man on Earth in a quarter mile. That level of dominance is unheard of in professional sports. It would be like Michael Jordan coming back in 2005 and winning another MVP award. However, the sport was changing around him. In the 70s, drag racing was a garageista sport. You could build a competitive car in your backyard with a welder and some tubing. By the late 80s, it was becoming corporate. Computer-aided design was entering the picture. Wind tunnels were being used. The budgets were skyrocketing into the millions. Garlits was an empiricist. He learned by doing. He learned by breaking things. But the new generation of engineers was learning by simulating. They were using computational fluid dynamics to model airflow. They were using data loggers, primitive computers strapped to the car to record drive shaft speed, exhaust gas temperatures, and clutch slip. Garlits hated computers. He famously said, "I have a computer, it's between my ears." But even he couldn't ignore the data. The rear-engine car, his baby, was being refined by people who had never welded a chassis in their lives. They were optimizing his design to the nth degree. And this is where the story shifts from man versus physics to man versus the future. The rear-engine design had solved the safety problem. It had solved the stability problem. But it created a new problem: parity. Because the rear-engine car was so stable and so predictable, it made the drivers less important. In a front-engine car, the driver was a hero. They were wrestling a bear. In a rear-engine car, if the setup was right, the driver was just a pilot. A monkey could drive it, some of the old guard said. That wasn't true. You still needed lightning reflexes, but the gap between a great driver and a good driver was shrinking. The car was doing more of the work. This democratization of speed meant that deep pockets started to win. If you could afford the best parts, the best data loggers, and the best wind tunnel time, you could build a car that was almost unbeatable, regardless of who was in the seat. Garlits, the independent tinkerer, started to find it harder to compete against the mega teams like Schumacher and Kalita. But he never stopped innovating. In the 90s, he started experimenting with monostrut wings, single-post rear wings to reduce drag. He played with different tire compounds. He even experimented with electric dragsters long before Elon Musk made electric cars cool. Now, let's pause and look at the anatomy of a modern top fuel run, the direct descendant of Swamp Rat 14. When a modern car launches, it hits 100 miles per hour in less than 0.8 seconds. That is faster than the blood can move in your body. Your vision grays out for a split second. The rear tires, which are wrinkled and deformed at the start, grow in diameter by inches as the centrifugal force stretches them. This changes the gear ratio on the fly. It's a chaotic ballet of physics. And sitting right in the middle of it, protected by a carbon fiber tub, is the driver. Their feet are safe. Their face is safe. If the engine explodes, and they still do spectacularly, the blast goes up and back, away from the cockpit. The firewall is a thick slab of titanium or ballistic composite. Every time you see a slow-motion replay of a top fuel engine letting go, turning into a fireball at 300 miles per hour, and the driver steering the car to a safe stop, you are seeing Don Garlits' hospital sketch in action. You are seeing the legacy of March 8, 1970. But there's a final twist to this engineering saga. The rear-engine car didn't just save lives, it saved the sport from being banned. In the late 60s and early 1970s, the fatality rate in drag racing was getting unacceptable. Insurance companies were threatening to pull coverage for tracks. The government was starting to sniff around. If the carnage had continued at the rate it was going in the front-engine era, top fuel might have been outlawed. It was simply too dangerous. By making the cars survivable, Garlits didn't just make them faster, he made them insurable. He made them palatable to corporate sponsors like Winston and Budweiser. You can't put a beer logo on a car that kills its driver every other weekend. It's bad PR. Here's the thing. When you strip away the branding and the corporate logos, a modern top fuel dragster is still fundamentally Swamp Rat 14. The materials are better. Carbon fiber instead of chromoly steel, titanium instead of aluminum, but the layout is identical. Engine in the back, driver in the front, giant tires pushing, tiny tires steering. It's the perfect design for going straight as fast as physics allows. And that's the genius of it. In a sport obsessed with innovation, where teams will spend millions to find 1/100th of a second, nobody has found a better place to put the driver. But let's talk about the specific engineering challenges that Garlits had to overcome to make this layout work, because they are fascinating. One of the biggest issues was the steering. In a front-engine car, the steering box was right next to the front axle. A solid steel shaft ran from the steering wheel directly to the box. Simple. Strong. In a rear-engine car, the driver is 15 feet away from the front wheels. You can't run a solid shaft that long without it flexing or binding. It would feel like steering with a rubber band. So Garlits and his team had to design a completely new steering system. They used a long, lightweight drag link made of thin wall tubing supported by bearings along the chassis. It had to be rigid enough to transmit steering inputs instantly, but light enough not to add dead weight. If you look closely at early rear-engine cars, you can see this long rod running down the side of the cockpit. It looks fragile, like a piece of spaghetti, but it was engineered to handle the immense loads of keeping a 2,000 horsepower car straight at 240 miles per hour. Another challenge was the fuel system. In a front-engine car, the fuel tank was right in front of the engine, often between the driver's legs. Gravity helped feed the massive fuel pump. In a rear-engine car, the tank had to be moved. They put it in the nose, way up front. This helps with weight distribution, keeping the front end down, but it created a plumbing nightmare. You now had to pump nitromethane 15 feet back to the engine, and you had to do it at a rate of 90 gallons per minute. That's like a fire hose. The fuel lines had to be massive, the pumps had to be stronger, and because the fuel has mass, sloshing became an issue. When the car launched at 4 Gs, the fuel in the long lines wanted to stay put. It would rush away from the engine, potentially starving it for a split second. A lean condition in a nitro engine is a death sentence. It melts pistons instantly. So they had to engineer baffles and check valves to keep the fuel moving in the right direction under extreme acceleration. Now you might be thinking, this sounds like a lot of work for a safety feature. And you'd be right. But remember, Garlits wasn't just building a safer car, he was building a faster car. The aerodynamic advantages were so huge that they justified all this complexity. By the late 1970s, the rear-engine revolution had spilled over into other classes. Funny cars, those wild, fiberglass-bodied coupes, started experimenting with rear engines. But here's where physics fought back. Funny cars have a short wheelbase. When you put the engine in the back of a short car, it becomes incredibly twitchy. It wants to spin like a top. The chain reaction and Dunn and Reith rear-engine funny cars were built, and they were fast, but they were terrifying to drive. They never caught on like the Dragsters did. The long wheelbase was the key to stability. This brings us to a critical realization about innovation. Context matters. Garlits' solution worked for top fuel because the rules allowed for unlimited wheelbase length. If the rules had capped the length at 150 inches, the rear-engine car might never have worked. It was the combination of the layout and the freedom to stretch the chassis that made it unbeatable. Let's fast forward to the 1980s. The sport had fully transitioned. The front-engine dragster was a relic, but a new threat emerged: blowovers. As speeds climbed past 260 miles per hour, the air under the car became a serious problem. If the nose lifted even a few inches, the air would catch it like a kite. The car would go vertical, 30 feet in the air, and then crash down. Garlits, ever the engineer, looked at this and realized they needed to manage the air under the car, not just over it. He started experimenting with ground effects, skirts and under trays that sucked the car to the track. He also refined the front wing, mounting it on a long, lightweight drag stock that was put out in clean air, ahead of the turbulence generated by the front wheels. This constant tinkering is what separated Garlits from his peers. Most drivers were just drivers. They showed up, drove the car, and went home. Garlits lived in the shop. He was welding, he was machining, he was thinking. He understood that the car was a living system, not just a collection of parts. In 1986, at the NHRA US Nationals, the biggest race of the year, Garlits showed up with Swamp Rat 30. It was a radical departure. The cockpit was fully enclosed with a canopy, like a fighter jet. This smoothed out the airflow over the driver's head, reducing drag even further. It also added a layer of safety. If the car rolled, the driver's arms couldn't flail out. The NHRA officials looked at it with suspicion. "Is it legal?" they asked. "Show me in the rulebook where it says it isn't," Garlits replied. They couldn't. He ran the car, and he won. Again. This canopy design is now standard on many top fuel cars. It took 30 years for the rest of the field to catch up to what Garlits was doing in 1986. That's the mark of true genius, seeing the obvious solution decades before anyone else accepts it. But let's get back to the human cost. What did this relentless pursuit of speed cost Don Garlits? His hearing is gone. Years of sitting in front of unmuffled headers will do that. His body is battered from crashes and fires. But his mind is sharp. He remembers every pass, every setup, every failure. There's a story he tells about the day he decided to retire for good. He was in his 60s. He was testing a new car. The G-forces were brutal. His vision blurred at the hit of the throttle, and he realized for the first time that the car was faster than he was. His brain could process the information, but his hands were just a fraction of a second too slow. He parked the car. He got out, and he walked away. He didn't crash, he didn't blow up, he just knew. The engineering had finally surpassed the biology. Here's what most people don't realize about the end of a racing career. It's usually tragic. A crash, an injury, a lack of money. For Garlits, it was a choice. He had built a machine so perfect, so fast, that he could no longer keep up with it. That is the ultimate victory for an engineer. You have designed yourself out of the equation. Today, if you go to a drag strip, you'll see the legacy of Don Garlits everywhere, not just in the top fuel cars. Look at the junior dragsters, the little half-scale cars for kids. They are all rear engine. Why? Safety. Parents want their kids to be safe. The design that was born from a catastrophic amputation is now protecting 8-year-olds learning to race. And it goes beyond drag racing. The principles of driver isolation and energy management that Garlits pioneered influence safety cells in IndyCar and Formula One. The idea that you build the car around the survival of the driver rather than fitting the driver into the gaps left by the engine is now a universal standard in motorsport. But let's not forget the sheer audacity of it. Imagine the scene in 1970. You're a guy from Florida with a blown-off foot. You're telling the titans of industry, Chrysler, Goodyear, and Hearst, that they're all wrong. You're telling them that the millions of dollars they've spent on front-engine R&D is wasted. You're betting your entire career, your reputation, and your remaining limbs on a drawing you made on a napkin. That takes a level of confidence that borders on delusion. But as the saying goes, the difference between delusion and genius is results. And Garlits had results. Now, consider the alternatives. What if Garlits had just retired? What if he had accepted the conventional wisdom that rear-engine cars didn't work? The sport would have stagnated. Drivers would have continued to get hurt. Maybe drag racing would have been banned in the 70s as too dangerous. Maybe it would have become a niche hobby for daredevils instead of a professional motorsport. The rear-engine revolution was a singularity. It was a point in time where everything changed. Before 1971, dragsters looked one way. After 1971, they looked another way. And they will look that way forever. You can't uninvent the wheel. You can't unlearn that putting the bomb behind you is better than putting it in front of you. This is where it gets really interesting. There are engineers today working on electric dragsters. Cars with 2,000 horsepower electric motors that make instant torque with zero lag. And guess where they're putting the motors? In the back. Guess where they're putting the batteries? In front of the motors, but behind the driver. The layout remains. The power source changes, the fuel changes, the materials change. But the architecture, the Garlits architecture, is eternal. It's rare in history that we can point to a single person and say they changed everything. Usually innovation is a group effort. The internet wasn't invented by one guy. The airplane was a race between many teams. But the rear-engine top-fuel dragster? That was Don Garlits. Sure, others tried, but he made it work. He made it win. He made it standard. And he did it with a limp. If you drive down Interstate 75 in Florida, just south of Ocala, you'll see a modest sign that simply says Don Garlits Museum of Drag Racing. It's a quiet place, filled with the smell of old rubber, oxidized aluminum, and history. But in the back, sitting silently under the halogen lights, is Swamp Rat 14. To the uninitiated, it looks like just another old race car. It's small, it's crude by today's standards. The wheelbase is short, the wing looks like a plank, and the tires are tiny compared to the massive slicks we see now. But if you know what you're looking at, it's like seeing the first wheel. It is the artifact that divided history into before and after. Look, standing in front of that car, you realize something profound. Innovation isn't usually about adding things, it's about removing barriers. The front engine layout was a barrier. It was a physical wall between the driver and the ultimate potential of the machine. Garlits didn't just move the engine, he removed the fear. Before 1971, every driver strapped in knowing they might burn. After 1971, they strapped in knowing they had a fighting chance. That psychological shift allowed them to push harder. It allowed the sport to grow from a weekend hobby into a multi-million-dollar spectacle. Now, you might be thinking, is the work done? Is the car perfect? The answer is no. The modern top-fuel dragster is currently stuck at a performance plateau. The tires can't take any more speed, the tracks are too short for 340-mile-per-hour runs to be safe, the engines are making so much power, nearly 11,000 horsepower, that the teams have to detune them just to get down the track without smoking the tires instantly. We are once again at a point where the physics is pushing back. The limiting factor isn't the engine location anymore. It's the tire compound. It's the glue on the track. It's the human body's ability to withstand 6 Gs of acceleration without the retinas detaching. But this time, because of Garlits, the engineers are solving these problems from a place of safety. They aren't solving them from a hospital bed. They're solving them with data, with simulation, and with the confidence that if they get it wrong, the driver will likely walk away. That safety net is truly Garlits' true gift to the sport. He took the penalty for failure, which used to be death or dismemberment, and reduced it to a financial cost. You break parts, not people. Let's look at the specific tech. The modern fuel system, the slide valve that controls the fuel curve, is a masterpiece of fluid dynamics. It mimics what Garlits was trying to do with his right foot, but with digital precision. It pours fuel into the cylinders at rates that would drown a normal engine, cooling the intake charge and preventing detonation. This is the granular level of detail that the rear engine platform allows. You can tune the clutch to the millisecond because the chassis is stable enough to respond to it. In a floppy front engine car, that level of tuning would be lost in the flex of the frame. Here's the thing. We often talk about disruptors in business. We talk about tech CEOs who changed the world with an app. But Don Garlits disrupted a world of steel and fire. He did it with a welder and a slide rule. He didn't have a team of software engineers. He had a few guys in a garage in Florida and a burning desire not to lose his other foot. That kind of visceral, survival-based innovation is rare. It's primal. It comes from a place of absolute necessity. And that's why this story matters to you, even if you don't care about cars. We all face front-engine problems in our lives. We all have systems or habits that are dangerous, inefficient, or just plain wrong, but we keep using them because that's how it's always been done. We keep the engine in front of us because everyone else does. It takes a shock, sometimes a painful one, to make us see the geometry clearly. It takes a moment of trauma to force us to redraw the blueprint. Garlits teaches us that when the machine is broken, you don't just fix the part that broke. You look at the whole design. You ask the hard question, is this entire layout wrong? And if the answer is yes, you have the courage to cut the chassis in half and start over. You have the courage to be laughed at. You have the courage to fail in public until you succeed. The 3.7-second passes you see on TV today, they're the echoes of that courage. The fire-breathing monsters that shake the ground, they're the direct descendants of Swamp Rat 14. Every driver who hugs their family after a race owes a debt to the man who refused to accept that part of the game meant getting hurt. If you've made it this far, you're clearly one of us. You're someone who appreciates the blood, sweat, and gears behind the glory. This channel exists to tell these stories, the ones about the mechanics, the mavericks, and the machines that changed the world. We don't just cover the stats, we cover the soul of the machine. So, the next time you see a dragster, don't just look at the flames. Look at the length. Look at the driver sitting safely in the nose guiding the missile. And remember that 50 years ago, a man looked at a catastrophic failure and saw a new beginning. He didn't just build a better car, he built a future. If you enjoyed this deep dive into the engineering of the rear engine revolution, do me a favor, click that subscribe button. It tells the algorithm that smart people like you want more content like this. Drop a comment below if you remember seeing the slingshots run, or if you've ever visited the museum in Ocala. Don Garlits is still out there, still tinkering, still thinking, and the sport he built is faster, safer, and louder than ever. That is a legacy worth celebrating. Thanks for watching Legacy Motoring. Keep your engine in the back, keep your eyes on the finish line, and I'll see you in the next one.